This webinar is, as I said, is part of a series that's based on a research project. It's a 4-year project funded by the AFRI program from the USDA, and it's a project where NC State and University of Georgia are partnering with Weyerhaeuser, Georgia Pacific, some other, and CASI, other agencies, and those of us at NC State and Georgia have done the on-the-ground research with the cooperation of our partners. And so these are the results we're presenting. And Dr. Larry Morris is a professor of soils in the Warnell School of Forestry at the University of Georgia. And I'm going to turn it over to him now to give you the presentation.
Well, thank you all for sitting in on the webinar today. And I appreciate you spending either your lunch hour or the hour just before lunch with us. So I was going to talk a little bit about soil impacts of biomass harvesting, and I'm going to put it a little bit into historical context and then talk a little bit about this specific project. And I didn't want to proceed without acknowledging my fellow professor Dan Markowitz at UGA, Eric Vance at NCASI, and particularly Christian Hoadley, who was a graduate student who spent a large amount of time in the field collecting some of these data over the last several years. So again, we wanted to ask a couple of questions sort of to set the stage for this webinar. And the first question I'd like you to think about, and again, there's not necessarily a right or wrong on this, but consider this statement. Biomass harvesting for energy production raises new concerns about sustainable forest management. Do you think this is largely true, largely false, or you're just not sure? I think Susan will publish the results.
Larry, while they're answering,
yes.
A couple people have commented that they're having trouble hearing. Is it possible for you to speak a bit louder?
Yes, I will try that. Okay? So again, if you can't hear me, send that information into Susan. We're having a little bit of technical difficulty with the audio, but I think we've got it mostly resolved. So our results are actually something that I thought might be the answer, but I was hoping not. Most of you think that the concerns that we have about biomass harvesting for energy production are largely new concerns. To some extent that is probably true, and then to some extent probably not as true as we may think. The second question I was hoping you might think about is this statement. Biomass harvesting for energy production will leave soil bare and susceptible to erosion and productivity loss. Again, simply answer true, false, or not sure. And Susan will publish the results for everyone. So the results suggest that most of you, the majority of you, really don't believe that we will leave a bare soil condition that is particularly susceptible to erosion and productivity loss. And we'll see some results from that in just a few minutes. The final question that I wanted you to consider is this. Biomass harvesting for energy production can reduce carbon emissions and the potential for global warming. Again, simply answer true, false, or not sure. And to be honest, our research has nothing to do with this. I was just curious. True. Okay, so there's a little bit of difference. A little bit more of you feel this is true than false, and again, a fair amount of you are really not sure, and that would be fairly consistent with what many of us think. Okay, so let's talk a little bit and kind of try to put what we're doing now into somewhat of a historical perspective. You know, when we think about biomass harvesting, what is it? It's simply woody biomass that is traditionally non-merchantable and left on site following a timber harvest is now going to be harvested. That may include, depending on the nature of the biomass harvest, foliage that would normally have been left on site. It might include branches, and it almost would always include non-merchantable stems and any large downed woody debris. And you know, just to put this again in context, if you look at here, this is a picture of a chopper, a roller drum chopper, that we don't see very much on sites any longer. But that is a good example of the type of woody debris that at one point was an obstruction to site preparation, and that now we would be considering removing in a bioenergy or biomass harvest. When we talk about biomass harvesting, it's important to recognize that it really is expected to be a major source of energy in the United States. If you look at all of the materials that are available, woody materials, it would include non-merchantable wood from traditional harvests. It might include residues from wood processing plants, mills. It might include materials from urban forests that now are largely going into compost or to, in some cases, landfills. And it might also include wood that we put in specifically for energy plantations. And there are really three issues that have tended to be the overriding issues associated with removal of woody biomass. The first of those is probably water quality. As we remove more materials, how does that affect water quality? We know that we have our best management practices that include streamside management zones in there largely for water quality, but these may or may not be effective when we have much more intensive biomass harvests. A second question that you've actually addressed in some of your earlier webinars in this series is how these biomass harvests might affect forest biodiversity and specifically wildlife habitat. And again, we've looked at some of these questions. I think Steve Castleberry did a webinar earlier, and I know that we've had several students looking at that as part of our project. And the third issue that has been around for quite a long time are some of these concerns of how we will affect the productivity of our forest sites. Because of these concerns, a number of states have adopted biomass harvesting guidelines. Kentucky, Maine, Pennsylvania, Minnesota, Wisconsin all have some sort of biomass harvesting guideline, and generally these guidelines are written in terms of how much of the woody biomass should be retained on site. And they range pretty much between 15 and 30% retention. Also, we have recommendations that were made by the Forest Guild for forest biomass retention and harvesting guidelines for the Southeast. The Guild recommended for Piedmont and coastal plain forests about 1 ton per acre as an absolute quantity be retained, and for all other forest types, about 3 tons per acre. It's actually somewhat difficult to reconcile these two sets of guidelines because, in fact, the retention targets in terms of percentage may or may not actually achieve that 1 or 3 tons per acre retention. So one of the questions I asked was associated with, is this a new concern, the productivity concerns with intensive biomass harvesting? And I would argue that it is a manifestation or a new manifestation of a concern that we've had for at least the last 50 years. In the 1960s, Keyes was studying Pinus radiata in Australia, and he reported declines when you went from the first rotation of Pinus radiata to the second rotation. That created some concern that somehow what was then considered just more intensive forest management and more intensive utilization of the mass that was growing in these forest plantations was affecting soil productivity. Later on in New Zealand, White reported quite similar declines. Based largely on these declines, or these decline reports, between about 1970 and 1990 in the United States, we had multiple investigations of how changing from traditional stem-only harvests, when we left the branches and foliage on site, as well as many small stems that were not going to go into either our pulp mills or our sawmills, we looked at how that compared with a complete tree harvest, where this would involve taking out all of the stems, all of the foliage, and all of the branches, and removing them off-site. In the southeast, we also were concerned about looking at how the addition of pine straw removal on a periodic basis to these forest harvests would affect soil productivity. Now, I would argue that although in one case we were removing the materials as part of the harvest operation, the primary harvest operation, there are some differences, but there are also a lot more similarities with coming back after the primary harvest operation and removing these non-merchantable materials. So I would argue that these concerns are not particularly new. So when we look at the site impacts of biomass harvest, including what we started looking at about 40 years ago, what were some of the things that we found? Well, the first thing that we found was that anything that resulted in increased soil erosion by removal of the forest floor and that protected litter cover was likely to be associated with a reduced productivity or reduced quality of the soil. Now, this is obviously not a picture from one of our forest operations, but it is a reminder that in the Piedmont and much of the southeast, our soils are quite strongly eroded already. They had a history of erosion. And our starting point for our planting and our productivity often deals with soils that are fairly infertile and suffering from soil physical conditions already. Anything we do that further exacerbates these problems is probably unacceptable from a long-term productivity standpoint. And clearly retaining forest floor protection on these sites is important. One of the other things that we looked at years ago in terms of these biomass harvests was how we maintained soil organic matter on the site, and what we did with that could be important in terms of long-term productivity and in terms of soil quality. What we found was often that the harvest itself had somewhat limited effects on soil organic matter, but because harvest and what we did for site preparation post-harvest were often linked, we would see that, some of the site preparation effects, particularly those that moved large amounts of slash, forest floor into piles, wind rolling. Here we're showing a KG blade working in Florida, were often associated with productivity declines and a decrease in soil quality. The third aspect of our research that was again repeated by a number of investigators over time was the idea that we did have to be concerned about balancing nutrient inputs and nutrient removals. And so in this graph, or this table rather, I show what nutrient inputs would be just from natural processes for nitrogen, phosphorus, potassium, and calcium on an annual basis. We roughly put in about 7 pounds per acre or 7 kilograms per hectare of nitrogen, about 1 kilogram per hectare of phosphorus, somewhere around 6 kilograms per hectare of potassium, as much as 15 kilograms per hectare of calcium in dusting precipitation that's associated with normal activities. Below that, I provide the information on loblolly pine in a loblolly pine plantation at age 22, the amounts of these nutrients that we removed in a traditional stem-only harvest, and those numbers are in black, and that would be for nitrogen about 57 kilograms per hectare, for phosphorus about 5, for potassium about 36, and for calcium about 51. And then in the green numbers, I provide what this means on an annual basis. And for the traditional stem harvest, we see that, basically inputs from natural processes exceed removals over a rotation on an annual basis. If we increase the harvest removal, so that might be a stemwood harvest with all of the biomass removed, the numbers are much greater. For nitrogen, 180 kilograms per hectare. For phosphorus, about 19. For potassium, about 90. And for calcium, about 180. And you can see that some of that green, that positive nutrient balance, becomes, either very marginal, as for phosphorus, or for the case of nitrogen, it actually becomes negative. So these negative balances are of concern to us in terms of long-term productivity. And they either have to be balanced by looking at reduced removals of high nutrient concentration material or fertilization. So they are important from the standpoint of long-term productivity. But I also include below corn in our area and the amounts of nutrients removed in corn. And if you look at those removals of 135, 20 for nitrogen, 24 kilograms per hectare for phosphorus, 34 kilograms per hectare for potassium, and these would be on an annual basis, we can see that even with the more severe types of removal for a forest harvest, we're still removing much less than an agricultural crop, and it means that we should be able to maintain that with just very low levels of fertilization. And the final thing that we learned from these studies on productivity associated with intensive forest management is that we have to maintain physical conditions of the soil. We have to avoid severe compaction, rutting, and other sorts of disturbance. To the extent that bioenergy harvests would result in working on sites that are under poor conditions where you would get rutting, you could increase that soil physical damage. The skid trails are important, and that photograph sort of in the middle on the right just shows that the short-term effects of this kind of physical damage can be manifested in growth of the subsequent plantation. So that's the final thing that we really can quite confidently point to, is that we want to avoid these physical degradation effects. Okay, so this is what we've learned, and then we wanted to put this in the context. If we do an operational biomass harvesting and we employ different levels of guidelines, how does it affect some of these conditions, and are these conditions affected to the point that we think that will have major effects on long-term productivity? So the specific objectives of the soils component of the biomass harvesting guidelines were, one, to provide an estimate of the coarse woody debris for different levels of biomass retention treatments. Again, when the biomass harvesting guidelines are written in terms of a percentage of the material remaining on site, it's not really obvious what that means in terms of actual woody debris left on site or debris left on site. We wanted to quantify the effects of different levels of biomass retention on concentrations of carbon, nitrogen in the forest floor, and mineral soil service. We wanted to determine if soil compaction levels differed among different levels of biomass retention. And we wanted to determine if soil disturbance associated from biomass harvesting operations and redistribution caused significant differences in soil stability and other soil characteristics other than compaction.
Larry?
The study was done in, yes?
Hi, there's a couple questions. Would you like to take those now?
Yes.
Okay, so the first question, is it
Sure. Put them up.
Is it presently feasible to remove 100% of biomass from a harvest site? Is anyone actually able to remove a high percentage of biomass with today's technology?
Absolutely not. In fact, one of the results that I'll be presenting in a few minutes, that even when we try to remove on an operational basis all of the biomass, all of the woody biomass, you will see that we leave quite a lot of that biomass behind. So the answer is no. It's not technically feasible.
Okay, thank you. The next question is...
What's the second question?
The second question is, are there any concerns about stormwater runoff management with this biomass harvesting?
At this point, it appears that the normal BMPs that we utilize are sufficient for biomass harvesting as well. And again, I will present a little data that suggests this, but if we look at the soil impacts of the biomass harvesting beyond what we get for normal harvesting, we don't see enough compaction difference or removal of the forest floor to suggest that we're going to really have surface runoff. The soil conditions from a physical standpoint are not greatly impacted.
Okay, thank you.
You're welcome. So just to kind of, I know that kind of puts the work we did in context, and this is how we actually did the study. We actually had two study sites. We had a study site in North Carolina that was in a 36-year-old pinus loblolly pine plantation that had been managed for saw timber production. It was 36 years old at the time of harvest. It had had 2 thinning treatments during the rotation. And as southern pine plantations go, it would be the kind of condition that would lend itself to having the most amount of woody biomass that might come back and be harvested or left on site. So it pretty much defined one end of the spectrum. The study site itself in North Carolina was located predominantly on poorly drained soils, bay burrow, pantagos, and leaf, and it actually had some drainage in it to indicate the poor drainage. We did a second study area in Georgia. The Georgia study sites were a little bit better drained. They were on spodosols and ulthasols. They were probably somewhat poorly drained on average, and the plantation was a little bit younger. I'm going to talk a little bit about both study sites today, but I'm primarily going to focus on the study work we did in North Carolina. The actual experimental plots were something that we don't really work with very much in soils research. We used a very large operational experimental plot. Each of the plots that we worked on was about 10 hectares in size. And if you compare that to what I would normally do for putting in a soil study of some sort of about a quarter-acre plot, it created probably much more operational conditions and much more variability to deal with. We had 6 biomass retention treatments. We had a study which is no BHG, where we had no biomass harvesting guidelines, and as a consequence, the operator was instructed to take anything that they could and bring it to the deck. So basically we got anything that was feasible to operationally collect in this part of the study. We had 2 retention levels, 15% retention and 30% retention of biomass, that sort of bracketed what you saw with some of the state biomass harvesting guidelines. And we spread the materials out from these 2 levels of retention in 2 ways. We could have it either retained and dispersed across the site, or we could have it retained and clustered into small piles on the site. So we had 30% retention and clustered, 30% retention dispersed, 15% retention clustered, and 15% retention dispersed. The idea of the clusters was that could actually provide additional habitat for small mammals and birds. It also might affect how the soils responded. And finally, we had a 6th condition, which was no biomass harvest at all. And in that case, all of the non-merchantable material was left on site. For the soils component of this, we had these large plots. We established 6 permanent plots that we located both physically on site and with GPS. And in these sites, we did our pre-harvest sampling in the before harvest stand, as well as post-site preparation sampling. Just to look at those small subplots, we did a number of things on those subplots to sample. We used a line intercept sampling method to basically run from the plot center out to the edges of the plots. And along this line sampling, we measured each piece of downed woody debris, both the length, the diameter, and from that we were able to estimate its mass. We sampled the forest floor and separated into the forest floor layer, the organic layers above the mineral soil. We sampled mineral soil from the surface to about exactly 15 centimeter depth. And we also took bulk density cores in that 0 to 15 centimeter depth increment. And here are some results from this first part of the study. On the left axis, I basically provided the volume of coarse woody debris in meters cubed to hectare, and I'll convert that in just a second. And I've given you the no biomass harvest, the 30% retention, the 30% both for clustered and dispersed, the 15% both for clustered and dispersed, and the no biomass harvesting guidelines. And there is quite a lot of variability about these mean values, but as you can see, that the biomass harvesting treatments that we imposed operationally actually made sense from a logical standpoint in what we were trying to remove. With no biomass harvesting guidelines, we left about 30 meters cubed per hectare of wood on site. With the no biomass harvesting, that was about 95 meters cubed per hectare of wood. To put that in terms of just mass, in terms of tons per acre, again, the pattern is exactly the same. So when we had the no biomass harvesting guideline, we left a little more than 5 tons per acre on the site. And when we had no biomass harvesting, there was a little more than 16 tons per acre on the site. Now earlier the question was asked, was it feasible to remove 100% of the biomass? I think this answers the question, that if you look, that under the no biomass harvesting guideline, we left over, really over 5 tons per acre of biomass out there, which is more than the 3 tons per acre that was recommended even for not southern pine plantations. So we leave quite a lot out there, even when we're not trying to. And that's really only the woody debris that is left dispersed across the site. One of the other concerns that was raised, or that has been raised in the past about biomass harvest and how it might affect the soil, is do we greatly disturb and destroy the forest floor, that important covering to prevent erosion. And so in this graph, what I've done is I've provided the pre-harvest mass in terms of megagrams per hectare of forest floor and the post-site preparation mass of those same components. Now pre-harvest, that consists, the forest floor would largely consist of litter, foliage, some bark, and some fine twigs that didn't get included in the woody component. And then if you see what happens post-site preparation, as much of the foliage, much of the woody debris comes down, bark is left on site, that there's actually an increase in what we would consider that forest floor. Also, you can notice that in the post-site preparation forest floor mass, that there really isn't a large amount of difference between the no biomass harvesting guidelines and the no biomass harvest at all, with the other treatments sort of lying in between. There's a lot of variability, and the amounts are large, the variability is large, but at least in 1 year following harvest, we don't see a real effect on forest floor mass among the biomass harvest retention treatments. So again, we're not destroying the forest floor, we're not destroying the protective covering. That goes back to, are we really concerned about increasing runoff and storm flow? Probably not a lot. As you might expect, and from the forest floor mass data, the forest floor carbon content follows basically the same pattern. It's just a simple conversion to go from forest floor mass to forest floor carbon. And we see again that there aren't large differences between the biomass harvest retention treatments and that post-site preparation, there's just a lot more materials in that forest floor fraction.
Larry?
Yes.
If we can go back to the forest floor mass slide, which is just one more there. The question is, what accounts for the increase in forest floor mass in the no biomass harvest site?
Okay. In the no biomass harvest site, what you get down on there is basically much of the foliage that didn't come off when you harvested the trees. You've got small brush, fine, small trees, pretty much everything that wasn't removed as part of the biomass harvest and was left behind as part of the normal merchantable harvest ends up being on that site. So you would actually expect the no biomass harvesting to have the highest amount of post-site preparation forest floor. And you might say that that's what's occurring, but to be perfectly honest, the variability is so high I would be reluctant to say that. But it's basically anything that wasn't removed as part of the normal harvest of merchantable stems gets left behind, it gets crushed and included as that forest floor or in the woody component. And most of the fine branches and most of the foliage ended up in the forest floor because, again, we're sampling this over 1 year after harvest. So a lot of that material has dropped off the branches if it was foliage. Small branches have been broken up and started adding to what would be considered that forest floor component. Does that answer the question?
I think so. And here's a related question, but what is the impact on organic matter in the forest with this biomass harvesting? So I think this relates to that as well.
Where in the forest?
Okay, well, I'll ask Carl to type in a clarification there. Why don't you go ahead and continue?
Okay. One of the other concerns that we have with intensive biomass harvest is what happens to the soil organic carbon, the soil organic carbon concentration. Again, we try to maintain organic matter in the soil. We know that we're getting a lot of materials perhaps added back to the forest floor, but are we having a lot of materials mineralizing from the surface soils? Again, this is the same type of graph where I presented the pre-harvest soil organic carbon content and the post-site preparation. So that's a little after 1 year after the harvest and site preparation. And what we see is that the actual differences in soil organic content before we ever harvested or did anything to the site are larger than the post-site preparation differences that might be associated with biomass harvesting guidelines. We also see a slight increase in post-site preparation soil organic carbon content. That increase I'll explain in the next graph, but basically there was no change in carbon concentration, but because we got some amount of compaction of the surface during trafficking, we actually had more soil mass to 15 centimeters depth, and the carbon contents increased proportionally.
Larry?
From a direct physical standpoint, we can also look at, yes.
Hi, yes, so that previous question that was asking about the impact on organic matter in the forest. So the clarifying question was where in the forest, and the response was where the biomass harvesting occurs.
There will be a reduction in organic matter content if you would look at the total amount of organic matter on the mineral soil in terms of forest floor and litter, and in terms of coarse woody debris. Because you're taking off some of that, you will have a reduction. But as we saw with the coarse woody debris, that reduction was from about 16 to 17 tons per acre on the North Carolina site down to about 5 tons per acre. So we only reduced that in total by about 10 or 11 tons per acre. That's what was being removed. There would probably be some small change in the mineralization in the carbon evolution from decomposition, but I'm going to show you some data in a few minutes that looks at mineralization and carbon loss as CO2, and we don't see large effects in the soil associated with treatments. So it's largely the 10 to 12 tons that are being removed as part of the bioenergy harvest that would really be the difference among treatments. I hope that answers.
Okay, well, I'll tell you what, we have about 15 minutes left, Larry, so I'm going to hold questions now until you finish presenting.
Okay, so let me go on. Okay, and then I'll stay as long as anyone has a question. So,
okay,
one
and
of the things
also
we were also
your
concerned
volume
with was the soil bulk density.
Yeah, can you increase your volume at all?
How's that? Yes, I can.
Good.
How's that?
That's
okay.
Good.
So one of the other questions that we have when we do any kind of more intensive treatment, whether it be harvest or bioenergy removal or biomass, is that we're running across the site with heavy machinery more, and we are liable to have compaction of the soil to a greater extent. So what these data show are the pre-harvest soil bulk density among the different treatments and the post-site preparation soil bulk density. And again, post-site preparation is important because that's the point we're planting at. First, you can see that there are not really many significant differences associated with the biomass harvest removal treatments. If we go from no biomass harvesting guidelines to no biomass harvest, we see that the soil bulk density ranges from about just shy of 0.9 grams per centimeter cubed up to a little over 1 gram per centimeter cubed. And again, the numbers are quite variable. What you do also see is that there was an increase in bulk density from pre-harvest conditions to post-harvest conditions that was largely associated with the harvest itself and not the biomass harvest that followed the original harvest. If I were to be asked, are these post-site preparation bulk densities biologically significant? Are they a problem? I would say that looking at the soil textures we were dealing with, that bulk densities in this bulk density range are not really any sort of concern from being root restricted in terms of growth. So that these bulk density changes are well within the range we would expect to be perfectly suitable for root growth. In fact, on these soils, I wouldn't consider bulk density to be root growth limiting until we were up about 1.4, maybe 1.45 grams per centimeter cubed. And all of these bulk densities are below that, and the differences among the biomass harvesting treatments are small. Finally, we were also concerned in just looking at some measure of overall soil disturbance. And what we did is we took some of the samples that we had collected for soil bulk density and ran textures on them. And what we did find is there was some churning of the soil, and when you churn these soils by operating on them when they're a little bit wet, what you'll do is you'll increase the fine particles in the surface soil because you'll take up more of the subsoil and sort of mix it in with the surface. And what we found that 18% of our samples actually had a change in particle size distribution, going from perhaps like loam to silt loam or loam to clay loam, and that this texture change was more common in the no biomass harvesting guidelines treatment when there was more operation. Again, this may have some significance. It's hard to say whether it's a negative effect or not. A small increase in the clay content or in the silt content is unlikely to have a major effect on productivity of these sites. Okay, so we've sort of went through this large study to look at the overall effects of our biomass harvest. But I did want to just spend the last few minutes talking about another study we did in association with this. And part of what we found is that any kind of harvest, including the biomass harvest, both disperses materials across the site or can create piles. The piles can be created just by gating or as part of the construction of a logging deck. They can be created by site preparation, machines moving across the site with maybe a V-shear on it, moving material into piles. Or in our case, we intentionally created piles for wildlife. And what we wanted to look at was the creation of these piles actually affect soil conditions adjacent to the piles. So our specific objectives of this component of the study were to determine if there's effect of harvest residue piles on soil properties and determine the relationship between residue pile size and distance from the pile on soil properties. So the study was conducted on the research blocks both in North Carolina and Georgia. We randomly chose 20 residue piles that had been previously classified as small, medium, and large. We set up a sampling protocol where we had the residue pile, and then immediately adjacent to the residue pile, we put in probes that took samples 1/2 meter away, 1 meter away, and then we placed a probe or took samples on the first bed, the first inner bed area, the second bed, the second inner bed area, the third bed, and the third inner bed area. We sampled the soil at 0 to 15 centimeter depth increments along each of those 9 points. We took measurements of soil respiration and soil moisture content at each of those 9 points. And we also looked at temperature gradients away from the pile at the first 5 points. This is giving you what that pile might actually look like on site. The pile here to the right was created during site preparation. There's a lot of coarse woody debris that got in that pile. And then you can see P1, P2, P3, those points that are right adjacent to the pile are moving away, the first bed and the second bed, interbed area, and then it goes out away from the pile. Each of these areas was outfitted with thermal buttons. We used a TDR measurement to look at the moisture content, and we used a gas sampler to look at carbon evolution as we moved from the pile. Again, trying to get some idea as to whether we were having an overall effect on the soil by construction of those piles. And these next 4 graphs are similar. In each of the graphs, we're going to have distance from the pile going from about 0 to about 10 meters, 30 feet, and we'll have the different values will be on the left. This one shows total organic carbon that we measured just by looking at soil samples. And what we found, somewhat to my surprise, that whether the piles were small, large, or medium, that we really didn't see a large shadow effect of that pile on either soil carbon or soil nitrogen. Material is moved into the piles, but there's not a lot of effect on the interpile areas of that material being moved. At least there's not a lot of relationship between distance to the pile and the amount of materials in those piles. This is the data from volumetric moisture content. We found that there were some effects of piles, okay, on the volumetric moisture content. We think that's because the piles either intercept rainfall and hold it in the pile, or it actually can help store evaporation, protect from evaporation in the spring. The results were inconsistent, but generally we saw, as in this graph depicts, either a small decrease in moisture content adjacent to the piles, and we largely think that's because the pile was basically collecting rainfall that never actually made it into the mineral soil. So they stayed wetter. Less rainfall made it to the soil beneath the pile. We also looked at temperature as we moved away from the pile. Again, we found that the piles had some effect, but those effects were generally small. But there was some shading effect of having that pile there, and as we moved away from the pile, there was more exposure to sun, and we had a slight increase in soil temperature. And finally, we looked at soil respiration as an index of overall microbial activity and the rate of processing within the soil. And what we found was that there was some increased respiration near the piles. That was probably a combination of effects on temperature, moisture, perhaps organic carbon, very likely soluble carbon that was being mineralized in the pile moving into the mineral soil. Again, this effect was significant across the two study sites. It was highly variable, and it was not particularly large. So that sort of gives the gist of the pile study we did. If we were to put overall conclusions onto what we found in our Biomass Harvesting Guidelines study, we found that the no biomass harvest left over 16 tons per acre, and that greater than 4 tons per acre was left on site when it was operationally harvested and the operator was told to take everything they could get. The forest floor mass and carbon content was increased more than twofold the first year following harvest, which certainly allays any fears that we're disturbing the forest floor and exposing mineral soil. Within the mineral soil, we saw no significant treatment effect on soil carbon or nitrogen concentration. There was actually a slight increase in carbon content within the surface 15 centimeters, and that increase was because we had some compaction and a greater soil mass within that 15 centimeters. We found that there was some soil compaction associated with harvest, but the levels of compaction did not differ among biomass removal treatments. The compaction we observed we would not consider growth restrictive. And there was some change in particle size distribution at the surface, which indicated some soil disturbance. Again, we don't particularly think this is a negative from the standpoint of long-term productivity or sustainability. If we look at the pile of harvest residues, how piling itself might affect the adjacent soils, we found that there was some small soil temperature impact and some increased microbial activity immediately adjacent to the piles. But overall, what I was surprised was the impact of creating piles had relatively small effects on adjacent soil properties, and these piles themselves were not a major source of post-site preparation variability in the adjacent mineral soil, although clearly they are an effect in terms of the distribution of the coarse woody debris. And with that, I see that I am about a minute from our scheduled completion, and I guess we have time for
Okay,
some
thank you,
questions.
Larry. Appreciate that presentation. First question, Carl's interested in, are there any concerns, any special concerns about biomass harvesting in riparian areas and also in steep slope areas as opposed to uplands?
Yeah, I think that whenever we deal with riparian areas, that they're riparian areas because they're adjacent to streams, and that increasing biomass harvest within those areas beyond, right now we have guidelines that suggest you leave material out there not leaving that material out there and taking it in the biomass harvesting guidelines would clearly increase erosion potential. And I don't think that, I'm trying to think of the different state biomass harvesting guidelines and those SMZs, but they're probably not a viable concern within SMZs, okay? I know we've done some work looking at like pesticide movement and sediment movement through SMZs, and anything that you do that really disturbs the forest floor, any kind of tracking in there, is likely to increase sediment movement not only from but through SMZs. In terms of steep slopes, I think that largely depends on the nature of the equipment used. If you were using some sort of a system that you basically were reaching into the SMZ, pulling materials out with an articulated arm and not skidding and disturbing the forest floor, it might be viable. Again, I would suspect it would depend on the nature of the equipment and the steepness of the slope. But I can't give an unqualified answer on that.
Okay, thank you. This question, I'm not quite sure I understand. Any concerns about the change in canopy cover with biomass harvesting, maybe meaning in the next forest that regenerates?
I'm not entirely sure I understand the question either.
Okay.
I'll answer it with a general comment that typically the harvest itself is only part of a harvest and regeneration treatment. Generally, what is done during site preparation will have much more effect on the subsequent stand than the harvest themselves. For instance, if I were to do a more intensive biomass harvest, but by doing that biomass harvest, I never had to put a do any shearing and piling on the site because I could put a bedding plow through it because there was very little residual slash. I think the net effect of the biomass harvest would be an improvement in soil quality. If the biomass harvest was done so that it required greater site preparation, greater amounts of shearing, and greater piling, or made it less effective in terms of doing some of the other treatments, it might have a negative effect. It's very difficult to separate the harvest from the site preparation operation. But typically I think the site preparation operation has a greater effect on the subsequent canopy than the harvest itself.
Okay. In general, on this site, it appears biomass harvesting had minimum impact on the soil. But what would you expect on a sandy soil?
We've always kind of gone with the idea that on a sandy soil, you're trying to maintaining organic matter is the greatest concern. So that, removal of that organic matter could be a problem. Again, that if we look even on this very productive North Carolina site, the difference in the amount of organic matter we left on the site between the biomass harvest, where we did as complete a job as we could, and the no biomass harvest, was about 12 tons per acre, or maybe a little less than that. On a sandy site that's probably fairly well drained, we're maybe not be thinking of a lakeland, but maybe a troop or something. We're probably talking on a less productive site, and we're probably in the order of maybe 5 or 6 tons per acre of biomass. My guess is we would probably from a stewardship standpoint, more value on the site leaving that biomass than taking that small amount of biomass off.
Great, thank you. A question on the pile study. The piles appear to have soil as well as woody debris in them. Was this affecting the soil productivity when when the topsoil was moved into the piles?
Well, this is one I just it's a site preparation question, and it's not really a biomass harvesting question.
Okay.
But I think I'm still hold the record of being the only one that's ever actually gone through any of the windrows created during site preparation with a chainsaw and sieved everything out. So I would say that there's more soil probably in many of these piles than there actually is wood on a mass basis. And that, yes, moving any soil into those piles would have some long-term effect on productivity. The data is somewhat equivocal on that because when we do piling operations, we often get better planting jobs, better bedding, and other things that tend to promote better growth in the subsequent plantation. But moving soil into the piles is completely unnecessary, and you can't help but think it has negative effects. And you can, even when you're just trying to move the wood, you can often move a large amount of soil.
Okay, and I'm going to try to fit in one more question. Helene has posted the exit survey for the CEU folks. If you have to leave now, that's fine. Larry, the question is, or will you have a future study to test your assumptions about whether the small observed impacts on the soil have detectable impacts on tree regrowth rates?
Yeah, this is, I mean, part of this is only really 1 year data, and we have planned to go back and to resample at a later date, 4 years in and 7 years in, to look at both regrowth and soil properties, because you can get an immediate impact of these treatments, but a lot of what happens over time, and this is one of the difficulties with doing these sorts of large studies. One of the reasons we permanently marked our subsampling plots was so we could go back, get to the exact site, and resample in the future.
Great. Well, that's about all of our questions. And we thank you so much, Larry, for presenting to us today. And thank you all for attending. Again, the link is in the chat box for you to take the quiz to get your credits. So with that, we'll sign off.
Okay, thank you very much. I appreciated the opportunity.
Thank you. I'm going to push it out too.